So reaction mechanism 12 is going to allow us to keep moving through this group of four reaction mechanisms that are related. So 10, 11, 12, and 13. And what we're going to see here is that they are all related to taking the connections that we made to both cyclized sugars and then to polymerized sugars, and now we're doing the reversal of that. So early on we had four mechanisms that dealt with doing those chemistries with aldehydes and ketones to make first hemiacetals and hemiketals, and then acetals and ketals, so four mechanisms that dealt with that. And now we have the four mechanisms that are reversing those reactions. So again, this is another reversal reaction mechanism. And again, just a couple of things to highlight. I always try to have something new that's different and unique to comment on with each reaction mechanism. With this one, again, just to highlight that sometimes we need to be looking for hidden functional groups, right? Sometimes you might not be sometimes you might just be looking at a molecule. You need to learn to recognize kind of what are maybe some hidden functional groups, some latent functional groups, if you will, right? We know that there's reactivity with aldehydes and ketones, but we need to realize when we see a hemiacetal or a hemiketal, that means we're kind of one step away from having that reactive functional group. And so remember, when we take aldehydes and ketones as they're present in sugars and we cyclize those sugars and make them into hemiacetals or hemiketals, we're really biochemically protecting those molecules. And so what they are one step kind of removed from having that reactive functional group again. And again, this is chemistry that we're going to highlight much more in detail when we go on to study carbohydrate chemistry. But let's go ahead and get started with the reaction mechanism that we're going to see here. So hopefully we're seeing some themes that are consistent here. So again, we have an a hemiacetal here, and we essentially want to take and we're going to swap out this OR group, have it leave, and we're going to reform a carbonyl here. And so if we want to have this guy leave, we want to have him be protonated. So we're going to have a base here that could help protonate. And draw out my lone pairs on that oxygen atom because I know what my next step is going to be here. Now we're going to have these lone pair of electrons come down, form a double bond between that carbon and that oxygen. Our leaving group, now being protonated, easily departs, and we're left with an intermediate here. And we've eliminated this alcohol. So don't get stuck in kind of a cyclical reaction, because remember, a lot of times we've seen this guy and we say, oh, that's a great electrophile, so we want to have something kind of come in and react here. Well, be careful in doing that, because we don't want to take and move this reaction mechanism backwards here, only because we know we want to end up with an aldehyde. So keep in mind that in most cases you're going to know the product that we're going towards, so that you know what the next step needs to be. And in that case, it's simply deprotonation of this protonated aldehyde to generate our final product. So pretty simple mechanism, pretty straightforward, just reminding you, just because we see something that's a great electrophile doesn't necessarily mean we're going to see chemistry at that carbonyl. That would take us away from getting to the target product, which in this case, they tell us is an aldehyde. So kind of the extra story that's part of this mechanism is reminding us to think about protonation states. We've done a lot to think about pH and pKa considerations to think about what the protonation state might be, and we want to make sure that we apply that in our reaction mechanisms. So I'm going to kind of go ahead and show you a situation here which sometimes I've seen when students do this reaction mechanism. Is we're going to have this OH group here, and we're going to have a leaving group that has been protonated. So this looks very similar to what we had on the prior page, but sometimes what students will do is they'll try to have this sort of happen in kind of a stepwise fashion, where we know that we want to have electrons sort of come down here, but rather than having them come down in, say, a concerted step like we had right here, they're trying to deprotonate here first. Right? This deprotonation step actually is going to happen here. So the order of these protonation and deprotonation steps matters. So let's take a look at what would happen if we did this deprotonation step first. We get to this intermediate. Now, the problem with this intermediate is we've got a species that has both positive and negative charges with it. So we have to be really careful if that's something that we're doing, and we have to do a pKa sort of analysis to see if that's something that's reasonable. So for example, we've got an alcohol here. Know the pKa for alcohols is 15 to 16. And then down below, we actually have a protonated ether. Protonated ethers actually have pKa's that are less than 0, very, very acidic molecules. It takes a fairly acidic environment to protonate an ether there. So what we're saying here has happened is that we were basic enough to deprotonate an alcohol. So again, if you are able to deprotonate this alcohol, we're absolutely going to be able to do it here. Right? It's that whole situation of when we would look at those neutral sort of amino acids that people would draw. That's not going to happen from a protonation state, because we know if we are acidic or basic enough that we are going to deprotonate the protonated amine on an amino acid, making it an NH2 group, we are certainly basic enough to deprotonate the carboxylic acid, making that be negative. So again, drawing an amino acid that has no charge on it is not going to be feasible. But again, having an amino acid that has no net charge, because, and let me just kind of draw this out here so we can see, if we've got our protonated amine group here, and then our carboxylate group here on a generic amino acid, what we're saying is if we are basic enough to deprotonate this and make it an NH2, we're certainly basic enough to deprotonate this. But again, having a species like this that might be have no net charge, right? This positive charge over here might balance out with this negative charge here, and this molecule has no net charge, but it is not uncharged. So having these zwitterionic species is possible, but we really have to have a thorough examination of protonation states based on pKa and pH to truly evaluate that. And so again, this is kind of what we're talking about here. When we're doing this examination of pH and pKa values, think about whether or not you're going to really be effectively having cationic and anionic species in your mechanism. We just kind of talked about the example with the zwitterionic amino acid, and then again, that's a classic case where we are going to have both positive and negative charges. But generally, when we're doing these proton transfer events, consider yourself either being in a neutral positive environment if you're more acidic, or a neutral negative scenario if you're more basic. You're rarely going to have both cations and anions when you're doing these proton transfer events. Biochemically, we already kind of talked about this application. Refer back to reaction mechanism 10, but the chemistry that we're seeing here is chemistry that has application with carbohydrate cyclization when we form hemiacetal and hemiketals, and then polymerization when we form acetals and ketals. So this set of mechanisms, this 10, 11, 12, and 13, are really looking at the reversal of that. So going from acetals and ketals to their hemi flavors is going to be when we depolymerize sugars, or we break that glycosidic bond. And then going from those cyclized but unpolymerized sugars, those monomeric sugars, to the open chain form, those linear sugars having the reactive aldehyde and ketone functional groups, are going to be what we see when we do these last two mechanisms, generating the aldehydes and the ketones.